Hello, in this video, we're going to be looking at dimensional analysis. Before we get into that though, we're going to take a few steps back in your math career and look at some of the basic foundational things that are going to be required in order to do dimensional analysis. Now, looking at this first one, we have 5 times something is 5. And so 5 times something, that value has to be 1, right? It has to be 1. 5 times 1 is 5. You're like, duh, yeah, I get that. Negative 2/3 times something is negative 2/3. That value has to be 1. Now, I have the same 2 problems over here. Notice that I said value of 1. I did not say it has to be the number 1. Those are 2 different things. So if it has the value of 1, we can multiply it by that value and maintain the same thing. So 5 times something is 5 has to have a value of 1. 2 over 2 has a value of 1. 2 divided by 2. That would make it true. We could do 3 over 3. Anything divided by itself has a value of 1. And thus it makes that true, right? So if we're multiplying by something that has a value of 1, we're going to be in really good shape. Now take that elementary idea, that elementary understanding that we have here, and now we're going to apply it to dimensional analysis. So looking at this problem, we see that it's 53 centimeters is equal to how many meters? The first thing I notice on this is the equal sign. We're saying that this left side is equivalent, it's equal to the right side. And so when we're going through this, we're not changing anything, we're just changing how it looks. Kind of like 2 over 2 is equal to 1. They have the same value. This 53 centimeters has the same value of some kind of amount of meters. And so the first thing I would do is I would take this 53 centimeters and I'd put it over 1. Now, we need to multiply by something that's going to be equivalent to 1. When I think about this, I think about 1 meter over 1 meter. That's equivalent to 1. Now, this we could multiply through. It's not going to be very helpful though, because we're going to have a lot of different variables going on here. The variable that we're trying to get to is meters, and more specifically meters on top and of this fraction. So this meters right here needs to stay so that meters maintains its position on top. This centimeters needs to be canceled with something down below. So instead of writing 1 meter, I'm just going to do a substitution, and I'm going to say I know that 100 centimeters is in 1 meter. So this is still equivalent to 1, right? We're not changing the value of it. We're just substituting in so it looks a little bit different to our advantage. Now, when I multiply this across the top, 53 centimeters, this label, this unit kind of is like a variable. You can kind of treat it like a variable, like cm as 1 variable. And then it's times 1 times meters. And then on the bottom, it's 1 times 100 centimeters. What we know is if this is all multiplication, we can divide things individually. So centimeters divided by centimeters would be 1, anything divided by itself. And then if we do the multiplication across the top, we get 53 meters. And on the bottom, we get 100. Now we're not quite finished yet, because 53 over 100, we can actually write that a little bit better. And this is where place value comes in. So we would read this as 53 hundredths, which is the same as 0.53. 5 being in the tenths place, 3 being in the hundredths place. So what we're saying here is that 53 centimeters is equivalent, it's equal to 0.53 meters. And so as we're going through this, keep in mind, we're not changing the value, we're just changing the unit of measure for a reason that would be helpful for us. So 53 centimeters is the same as 0.53 meters. It's the same distance. We have one more example. 3 liters, and we're trying to convert it to a certain amount of milliliters. Same value, 3 liters, think 2-liter bottle of soda and then half of another one. How many milliliters is that? How much is it equal to? And so I'm gonna do the same process, 3 liters divided by 1. And then I'm gonna think about what's a value that's equivalent to 1 that I can multiply by here. And I think of 1 liter over 1 liter. Now I'm thinking ahead here, and I want this to be milliliters on top. So if I want milliliters on top, right now I only have liters. So I need to do this, instead of 1 liter, I know that that's 1,000 milliliters. And I also see, looking ahead, that like this liter and this liter will simplify down. So those are kind of thought processes I go through, knowing what's gonna happen when I multiply this through. So this is still equivalent to 1. 1,000 milliliters divided by 1 liter that's still 1. We just did a quick substitution. Let's multiply it out. 3 liters times 1,000 milliliters, 1 times 1 liter. Things that simplify down, the liters simplify to 1. On top, we end up with 3,000 milliliters. And since the bottom is just 1, we don't write that. So we're at 3,000 milliliters. The last thing I would do on any of these problems is to kind of just think about what we know about these units, and does this make sense? 3 liters. 3 liters are large units of measure, right? 3 liter bottle. There's gonna be a lot of milliliters that are gonna make that up, milliliter being a very small amount of measurement. So it would make sense that 3,000 milliliters is equivalent, it's the same as 3 liters. So this is why if you were looking at like a pool or even a bottle of soda, they don't measure it in milliliters most of the time, because there's a larger unit that can measure that and to give us a better idea of what that value is. But we could really say either one, they're equivalent. And so those are the basics of dimensional analysis and using the math that's involved to stay mathematically sound through the process.